Hi everyone, and my name is Vandana. I'm a grad student at Purdue University. Today I'm going to be telling everyone a little bit about the work we've been doing to uncover and trace the large scale structure at high redshift in 3 dimensions. And specifically, I'm going to be telling you about this one very interesting and very extreme structure we've identified at redshift 3.1. Let's get into it. So, first of all, this presentation is titled Unveiling a Proto Supercluster, right? So, a proto supercluster is, in fact, an association of protoclusters. It is a cluster of protoclusters. But then, what is a protocluster? Well, a protocluster is the high redshift progenitor of a present day massive cluster of galaxies. These are extremely extended and unvarialized structures, which we see at redshift greater than 2. And the typical kind of appearance of a protocluster and its evolution to become a redshift 0 cluster, you can kind of see it visualized in this image to the right. Right. So, great. Why do we want to study these protoclusters? Well, because we actually know very little about protoclusters compared to their low redshift counterparts. For example, one of the things we have seen through some limited observations of protoclusters is that they tend to host extremely elevated star formation rates. And this is very much in contrast to clusters at low redshift, where we see that the galaxies within clusters are more likely to have C star formation and to have quenched. And this is a very well-known result, which has been known for several decades, right? So protoclusters are very different to their low redshift counterparts, but we don't have a very clear idea of why. So the idea is that this very high star formation rate in protoclusters should be a result of them actively assembling their mass, right? But then where is the gas to fuel this mass assembly coming from? So this kind of raises the question, how are protoclusters connected to the cosmic web around them? How are like the cosmic filaments they're connected to feeding them gas, right? Another question you may ask is, how are protoclusters affecting the galaxies within? So how does like the very active star formation in these high redshift protoclusters completely quenched by redshift 0 so that they look like the clusters we see today? So that kind of raises the question of, where are these extremely star forming galaxies, or where are the extremely massive galaxies, which are the progenitors of brightest cluster galaxies today, located within the protocluster volume? And as you can imagine, all of these questions kind of require a very clear 3D perspective of protoclusters to answer, but then they also require a pretty substantial sample of protoclusters so that we can kind of analyze these questions in a statistical way. So, the work I have been doing specifically is as part of the Odin survey. Odin, or the 100 degrees squared DECAM imaging in narrowband survey, is a wide area, deep narrowband survey, which is seeking to identify protoclusters at 3 redshifts around cosmic noon as overdensities of Lyman alpha emitters, or LAEs. The idea being that with a narrowband filter, you will see an excess in the narrowband flux over the broadband flux when the Lyman alpha line is shifted into the narrowband window. So for galaxies in a very specific redshift range, right? Um, the narrow the narrow width of the Odin filters is kind of useful because it allows us to sample a very thin slice of the universe, right? And because it's a very thin slice, because the line of sight distance you're looking at is quite small, the 2D distribution of matter is actually pretty close to the 3D distribution, right? And this can be very useful for identifying these protoclusters, because if you have a very large line of sight distance, then foreground or background interlopers can make it very hard to identify where there are overdensities of galaxies corresponding to these massive structures. So Odin has identified about 40 protocluster candidates at redshift 3.1 in the extended cosmic field, and in the extended cosmos field. And among the protocluster candidates we've identified, there is one particular region in the surface density map of the LAEs which kind of jumps out, right? And that's the region highlighted in the red box here. So in this region, we have multiple closely associated protoclusters spanning an almost 1 degree squared region, right? And so we have called this a protocluster complex, and we've designated this complex Cosmos Z3.1a. Um, and this is one of the most extreme LAE overdensities the Oden survey has identified till date, across approximately 4 field and filter combinations. So across an area of almost 40 square degrees of the sky, that is. So we've undertaken systematic follow-up of this extremely extended complex, Cosmos Z3.1a. We've confirmed more than 300 LAEs in that region through a combination of targeted Keck Deimos spectroscopy and wide area DESI spectroscopy. And you can see these confirmed sources in the right panel of the figure. I think, or I hope it's evident just by looking at the kind of the colors of these sources when they're color coded by redshift, that sources which are close together in the sky also seem to have similar redshifts, right? So this on its own already makes it seem like this structure is real. It is not due to chance alignment of galaxies, but rather this is a very legitimate overdensity, right? So with these spectroscopically confirmed galaxies, we've set out to actually reconstruct the large-scale structure in 3 dimensions. And so motivated by what I said earlier, the fact that just looking at the redshifts of the sources, it looks like sources which are nearby in projection are also nearby along the line of sight. We've developed a probabilistic method wherein we use the line of sight positions of confirmed LAEs as a prior. And we use that to kind of probabilistically assign positions to the unconfirmed LAEs. And again, this is also because we expect all of our LAEs to be within a relatively narrow line of sight range, right? So, so we use this method to leverage the full LAE sample beyond, like, using all sources which we've selected both through their photometric narrowband flux access, and then also the ones which we've actually followed up and confirmed with spectroscopy. To know whether or not this method is valid, we carried out some very detailed tests with the lustrous TNG simulation. And we did find that using this probabilistic method to leverage the full LE sample, we have a statistical improvement in the reconstruction of the 3D structure, measured by comparing to the dark matter simulation, which is a kind of ground truth which we have to compare to in the simulation. In the interest of time, I'm not really going to go into the details of the testing we did, but if anyone is interested, I would be happy to explain it more at the end of the presentation. So based on our 3D reconstruction methodology, this is the 3D density map, which we've obtained for Cosmos Z3.1a. So these green spheres within Cosmos Z3.1a, within the 3D reconstruction, correspond to extended and luminous Lyman alpha nebulae, or Lyman alpha blobs, LABs. You can see to the right a few images of what these LABs look like. These LABs were also detected in the same narrowband imaging, and their typical size is 100 moving kiloparsecs or more, right? So this is much larger than the scale of a single galaxy at high redshift. So these Lyman alpha blobs were not very clear on their origin, although their proposed origins include AGN fueling, or sorry, we're not very clear on where the energy for this extended Lyman alpha emission is coming from. But the sources include AGN activity and extremely active star formation, and in my opinion, the most interesting option, which is gravitational cooling of cool gas inflowing into a massive halo, right? The position of the LABs within Cosmos 3.1a doesn't immediately answer the question as to what the source of energy for these LABs is, but it is interesting that they seem to systematically avoid the most overdense region while also being very closely associated with these LAE overdensities. And just for context, the number of Lyman alpha blobs we see in this one region is 4 times higher than what we see in other more unremarkable areas of the cosmos field. So this is very interesting, right? And this behavior is not unique to this particular complex. So this is another complex, Cosmos 3.1c, which is within the same field, which we followed up with some pretty extensive GMOS, Gemini GMOS spectroscopy. And again, you can kind of see that the LABs seem to avoid the most overdense regions. And another feature, which you can see both from this reconstruction and from that of 3.1a, is that the large scale structure at high redshift is very, very irregular. It's kind of not at all spherical, right? And it is seemingly having a preferential axis along which it's elongated, which kind of highlights the importance of sightline, right? When you're looking at a structure, it might look very drastically different according to which axis you're observing it along.
Vandana, you're running low on time, so could you try to wrap up?
Uh-huh. So finally, getting to the actual title of this structure, Cosmos C 3.1a as a proto-supercluster. So from our 3D density map, we actually identified multiple distinct peaks in the density map, right? 10 density peaks in total. And each one of these density peaks has an estimated descendant mass greater than 10 to the power 14. So each one of these is probably going to evolve into a cluster, right? So this is what makes us classify Cosmos 3.1a as a proto-supercluster. The only other known example of such a structure is Hyperion at redshift 2.4, so at a later cosmic epoch. And so this is like a really fascinating example of a very extreme structure observed at pretty high redshift. So I will leave my summary up here and I'm happy to take any questions.